So today we're going to continue with the Fortran lecture. And I looked into my notes and I realized that I didn't go through a special kind of data type, which we haven't, which is also important in Fortran, and it's called derived data types. And these are data types that you can define yourself, and sometimes you can't fit everything into an array. You probably want some more rich data types in your code. And Fortran provides you with a data type called derived data types for that purpose. And a derived data type can combine standard variable types like integer, real, logical, characters, arrays into a single new data type. So it's kind of a compound data type. It's very similar to what we did in Python with object-oriented programming. So we, in that case, we combined data and also functions in this case, but just derived data type is only a combination of several variables that are grouped together in a single data type. In Fortran, you define a new derived data type by using a type statement block, which describes all your compound data types inside that that should be contained in that data derived data type. And then basically you can use this defined data type as just like any normal variable declaration in Fortran. And the only difference is that you have to use the keyword type and then a parenthesis, and then you give your name of your newly defined derived data type. So here we have, let's see here. So in this case here, we have a program here that defines a particle data type here. So this is our new data type. And this data type combines 4 fields. So you have an X, Y, and Z field, and then mass. So this is just a simple example. And that will become a single data type. So in this case, you can declare a particle as a new variable. And that you do with this declaration. You use the keyword type, and then you specify the name of your data type that you have defined earlier, and then you give it a variable name. In this case, I give it the variable name P. And then you can use this as a variable. And the fields that are contained inside the data type are accessed by using the % operator. So to access the X field in the particle data type, you type P%X and then assign that value. So in Python, this is usually done using the dot notation, but dot is kind of difficult to redefine in Fortran, so they chose to have the % operator instead of the dot operator, which kind of looks a bit odd, but we have to live with that. And then you can access these like variables by also the dot operator and just referencing the field inside your data type. You're not limited to single data type, as I said before. You can have multiple data types in a single derived data type. So in this case here, I have a data type called data record, which contains some data that I want to store as a single record. And here I have a floating point variable, I have an integer, a logical, and a character data type. And I declare it here using type data record D. And then I can just assign the fields of the D variable, my fields that I have in my data type. And I can print them like normally. So you can combine any data type here. You can also have other arrays and also other derived data inside a data record. So you can create quite complex data structures using this, using derived data types. It's described in my book as well, or the online book, so you can read more about it there. I've also updated examples to contain this. I will provide that updated zip file later on with these examples as well. So let's continue here. So something about the structure of Fortran code. So you have shown before that main program in Fortran is a single file called with the keywords program, contains, and end program. And end signals the end of the program. And that is also the only required keyword you have to have in the Fortran code is end. Everything else is optional. And you can only have one of these in a project. So only one of your source code files can have program, contains, and end. There's also a way of stopping your code using the stop statement, and that will terminate the execution of your program. And this, you can call that from wherever in your code that you want, and it will stop the code. So I usually try to not kind of litter my program with stop statement, because for a user, or for example, if you write a library, if the user doesn't know that your subroutine will call a stop, you can kind of it's something that a user of your library doesn't expect. So I usually try to have that in some central point in my code. Subroutines can be both external, placed in separate source code files, implicit interface, and it can also be implemented in other languages. So basically you compile them separately to object files, and then those are linked together. So actually the language doesn't kind of matter in this case. However, you have to be aware of that C and Fortran, for example, have different calling conventions. So there are some issues regarding calling C routines from Fortran, because Fortran, for example, all the parameters in the subroutine are reference-based, which in C, scalar values are always passed by value. So you need to kind of take care of that when you call. But basically, you can combine both Fortran and C code using this method. Internal subroutines are subroutines that are placed in the contain section of either your program, main program, or in a module. But you can also have subroutines inside of functions. So you can hide, you can divide up a function in smaller function subroutines, which can be placed inside the function or subroutine itself. And then you can have subroutines in modules. So subroutines are defined using the subroutine keyword, and then you give it a name. And then you give it a parenthesis and argument list of variables that can be passed to the subroutine. It's very similar to Python. However, you need to declare all your variables afterwards. So you need to kind of put in directly after declaration, you give all your input arguments and data types. You can exit the subroutine using return. It's optional. You don't have to use return. If your routine comes to the end subroutine, it will exit automatically. You can have return in multiple locations in the subroutine that will always exit the subroutine. You don't have to. You can end your subroutine using end subroutine, and it's optional to have the name of the subroutine at the end as well. I usually do it because if you have a longer subroutine that covers multiple screens, it could be a good idea to have the subroutine name at the end as well. Also, variables passed to subroutine are passed by reference. So the subroutine, so when you pass a variable from a main program to subroutine and you modify into this in the subroutine, it will modify the variable in the main program as well. So that is, you have to be a bit careful. This is done to be efficient and fast. Fortran is always about being as fast as possible. Copying variables over takes time, so that's why everything is by reference. You have to declare your arguments in the subroutine. You call your subroutine using the call statement, and control is returned using the return statement. And you can have, as I said before, several return statements in your subroutine. This is an example of how this works. So I've declared an integer a in my main program, two-dimensional array b, and one-dimensional array C. And then I call my procedure and I pass my variables over, and they are passed into the routine. And you have to declare them in your subroutine as well. And in this case, you also have to kind of pass, in this way of calling subroutines, you need to pass the sizes as well of the arrays that you have in your call. So in this case, the integer A denotes the size of B, for example, and you declare that as well. The last dimension is you don't have to call, because that is not needed to get to the next column, so to speak. Functions are similar, but here you also declare a type, return value type for the function. So it's very similar to Python as well. And then to actually assign the return value, you just assign the name of the function, the value that you want to return. And this is how a function can look like. So this is I defined a floating point function f of x, and then I assign f here, which is the function name, and that will be assigned the external variable y. We'll get a value from that. So modules is a concept that was introduced with Fortran 90, and it's very similar to modules in Python. They can contain global data that is available, variables that are available from the module, and you can use in your calling program. You can define derived data types, subprograms, interface blocks, name list definitions for file handling. And the idea is that you package everything associated with some kind of task into a module. So for example, if you have interval arithmetic, you can put that in a single module. If you're from structural mechanics, like I am, you can put finite element functions of a certain type in a single module. So you collect them together in functional blocks. The module is very similar to the program definition. So you start with the keyword module, and then you give it a name. And then you can have variable declarations and different specification statements in the beginning. And then you have a contains section, which contains the subroutines of that module. So before contains, you can't have any subroutines. You can only have declarations like variables, derived data type definitions, and so on, and constants, of course. So below here is a very simple module here. There is no contains section. So we only declare two constants here, ik6, which is a selected real kind of position 6, and also rk, which is a selected real kind of 15,300, and assign those. So those will be contained in the module's constants. If you want to access those, you have to use, from your calling program, use the use statement and give the name constants afterwards. So here I say I want to use the module constants. Then all the declarations that are available done in constants will be available to my calling program. So now I can use the ik6 constant and my rk here. So this is a way, for example, to collect all your global declarations of a program in a single source code file, and you can use those in other parts of the program. It's a good idea not perhaps to have a lot of global variables in a module, because that will kind of create some kind of spaghetti. You don't know where the variables are coming from and so on. So, but constants and derived data type definitions is very good to put in modules. You can of course put subroutines inside modules as well. Then they have to be specified in the content or contain section. And here you can also actually decide which of these subroutines should be visible for the main program. So here I can use private and public to declare if a variable should be visible to the user. And you can also put private on a subroutine, so make sure that subroutine is not visible for a user of this module. So that could be used to hide implementation details of your algorithms, things that you want to be able to change, but you want to have it in subroutines inside the module for the subroutines to call inside the module without being used by the user, so to speak, the library user. Yeah, same thing here. You use truss, and now the bar2e command is available. I can call that from my main program. As I said, variables are passed by reference. You have to declare your parameters, but they actually don't have to be the same type as the calling routine. You can also have the last dimension can be left out for arrays. So here's an example here. I have a 4x4 array and a vector of 3 elements. And I call my subroutine here using the array A, and then the dimensions I pass along into the subroutine. Same thing for the vector here, 3. In the subroutine, I can actually interpret the array A as a one-dimensional vector. So I can take the rows and columns coming in and declare a vector A here, vector A with rows times columns in size. That's perfectly fine. So as Fortran, all the variables are passed by reference. This is just a memory pointer coming over here, and also memories for two-dimensional arrays is also stored like a one-dimensional vector in memory. So it's no problem as long as the total number of elements is correct. This will be perfectly legal code. You can have 2 flavors of interfaces. You can have external and implicit interfaces and internal explicit interfaces. So in Fortran 77, you only had one option, basically implicit interfaces, which consist of separately compiled F90 files, which required you to kind of keep track of the number of arguments you were calling in each subroutine, because the compiler could only see each separate source code file. So they couldn't kind of check for that you called it with the correct parameter. So you can, for example, call a subroutine with an integer parameter would expect a floating point. That would link together in some cases, and when you did that call, it will be the subroutine will only see garbage, and so that was a problem. In Fortran 90, we introduced an explicit calling convention. That means that there are some additional features when you're using modules or contain sections. The compiler actually can look at your code and also automatically handle some of these parameter exchanges. So you don't have, for example, specify the sizes of your arrays coming in. You can just pass arrays in to subroutine, and you can query that incoming parameter for the correct size. That makes it much easier and also less error prone when you're coding. So my recommendations is always use modules, always use program and contain sections. Never separately compile Fortran subroutines in single source code file. Always compile them in modules. The benefits of this is that arrays and vectors can be declared inside your subroutines using only the number of dimensions. So for example, one-dimensional vector can be declared by parentheses colon instead of specifying the exact size. Two-dimensional colon, comma, colon. Three-dimensional, you can have colon, comma, colon, comma, colon. And so on. And that will also lead to much smaller subroutine parameter lists. And you can query the arrays that comes into a subroutine using a similar way that you do in Python using len, for example. You can use size to query an array. So size will return you give it the parameter of your array and then the dimension you want to query, and then it returns you a scalar value of the number of elements in a certain dimension. So here, example here, we have my subroutine here. This is an implicit interface. This is separately compiled. You have to give rows and columns here to be able to specify the arrays coming in. Then you can use size here as well, because now these are kind of obviously that size. But you need to kind of make sure that these are correct and the declarations correspond here, and you have to pass the right arrays over that order of that certain dimension. So in this case, I actually have to specify 20 by 30 and have to specify the actual values here to be able to, for the subroutine to work. By using module interfaces instead. So in this case, I have created a module called utils, and I have said that I want to use this module here. I can declare my subroutine here using only a single parameter a, which is my array. I declare the array with colon, comma, colon here. So I know that I need to specify the number of dimensions of my array that is coming in. So in this case, it's a two-dimensional array. And now I directly can assign all my values here. I don't have to do any special declarations here. Also, the information about the array is also available here by specifying size a,1 and 2. And this is much nicer way of doing it. It's more like you do it in Python. You don't have to think about the array sizes. These are passed along with the array. This also works when you do, if you have a program and you don't have a module, you can, if you put the subroutines in the contains part of your main program, same rules apply. You can use colon, comma, colon here as well, and all this will work in the same way as it would be in a module. You can do this in using an explicit interface as well. You can separately compile these things again, but without using modules. But then you have to declare the interface here, which is something you would like to avoid because this is kind of complicated. So it's very easy to put in a module. You just create a new Fortran source code file using the module syntax and save that separately, and you get all these features for free. Another nice feature is something called automatic variables. So for example, if you have a subroutine that takes an array as an input and you need another array with the same size as the incoming array, you can automatically allocate this when you call a routine. And that is called automatic variables. Those are created on the stack, and the stack is a special smaller reserved memory area which is limited in size but very fast. So you have to be aware that you don't create too large arrays using this method, because then you can get you hit the stack limitations, which is system dependent and not always in your for your control. But for smaller things, it's perfectly fine. It's the fastest way of doing allocations, actually using automatic variables in subroutines. So in this case, I have my old subroutine again. Incoming array, 2 dimensions, A, and then I want a B array that is the same size. And then I can do declaration here, integer dimension size a,1, size a,2, and then declare B here. So B will have the same number of elements as A, and that will be automatically allocated on the heap. So something about arrays and what you can do in Fortran. So sometimes you don't know the size of the arrays at compile time, and you have the user of your program, for example, as a molecular simulation, he wants to use different kind of number of particles. He specifies that in input file, and your Fortran code will read that input file, and now you need to kind of make sure that you have room to simulate all these particles. In Fortran 77, there was no way of dynamically allocate the memory. What you have to do is actually pre-compute arrays and have them in certain sizes, and then access those arrays, which often led to the recompilation of your code depending on your problem size. So what you can do in Fortran is you can add a special attribute to your declaration called allocatable. And then you can, that means that you can, the sizes will determine, you can then allocate the number of elements dynamically in a separate statement. So you declare the dimensions of your arrays using the colon, comma, colon or colon notation, and then you use a special allocate statement to allocate the size of that array. So this is the way it works. So you add this allocatable attribute here. Instead of giving a explicit size, you give it just a colon here, and you give your variable f a name. And then a two-dimensional array, colon, comma, colon, and then a name here like this. And then you use the allocate statement here to actually set the size of your array here, in this case f20. So now it will allocate memory on the heap, which is memory that is managed by the operating system. So in this case, Fortran will also operating system. I need 20 elements, floating point elements of f here, and it will give you back a pointer to that memory location. And same thing with two-dimensional 20 by 20. You can do this in one go as well. You can put them on a single line. For if you want to do it more, you don't want to spend a lot of lines allocating variables, you can just do it separately. It will still do them after each other, so it's not done in parallel. Then it's very important when you're using dynamically allocated variables, you are responsible for deallocating them. So deallocate is used to remove memory used by a variable. This is especially important if you have a loop, for example, and you allocate a variable inside a loop and forget to deallocate it. It will reallocate this memory all the time. And after a certain number of loops, the program will fill the entire memory of your machine, and it will probably crash your program, or even harder, crash your machine. So it's important that you make sure that you have all variables are kind of paired. You have one allocate and one deallocate. And also try to avoid doing allocates inside loops, because this allocate is an expensive operation. It takes time for the operating system to allocate this memory. Not much, but it's much longer than declaring a variable with a fixed size in Fortran. So you should allocate large sizes of large arrays if you do this, because otherwise it could be very expensive. So many times you have an array and you want to call a subroutine with a part of that array. And in Fortran 90 and later you can have something called a subobject, and that is a way of extracting smaller parts of arrays which can be used to put in arguments or assign other variables. It's very similar. I already was into this using the index notation in when you used arrays before. So it's very similar to what you have in MATLAB. So in this case here, I have some variables here. I will see if I can open my example here. 22, yes. So I have a code here. I just fill it with numbers. And so first I just print out A. And you see here it's an array containing from 1 to 50 numbers. Next, I will do a subobject here. So I will have an array that is from the columns 1, 2, and then 5 to 10 columns. And now it is this different syntax from Python here. So 1 and 2 are included as in indexes. So it will go from 1 to 2 and 5 to 10, not 1 and minus n minus 1 here. So let's see what happens if we run this. So you see here now we have matrix A2, which is a 2x6 matrix, which should be 2 rows and 6 columns here. That's also correct. So I have 5, 6, 7, 8, 9, 10. And then I have 15, 16, 17, 18, 19, 20. So that seems to be working as well. I can extract a vector, then I just set a row here, and then the columns. This will be a vector. So now you have vector A2 here, 5, 6, 7, 8, 9, 10. So 5, 6, 7, 8, 9, 10 here in the global array, like this. You can before you can have colon here, and then it will have all the rows and columns 5 to 10. So now we have all the rows here. So from 5, 15, 25, 35, 45, and going up to 10 here. So this is this part here, which I extracted from A. It's also possible to give non-continuous indexes. So in this case, I have 1 and 3 and 2 and 4 here. I'll just comment out. You should also be aware that some of these index operations can involve copying. So sometimes they can't, Fortran can't kind of figure out a way of passing this information over without doing a copy. So this should be done for perhaps smaller arrays, not millions of lines, rows or columns. So just be aware of that. So now you see here we have 1, rows 1, columns 2, so that is 2. And then we have 3, which is 22 here. So that one here and this one here. And then we have 24 and 4 here. So you see here, I extracted a sub array that consists of 2, 22, 4, and 24. So that is a nice way of being able to extracting things from arrays and passing them along to subroutines that require other sizes, or you have to assign a variable that is smaller with information from a larger array. So it's a nice feature. There's also built-in matrix multiplication and scalar products. So you could multiply arrays before using the standard Fortran operator, but the standard Fortran operator is element-wise multiplication. So if you want to do matrix multiplication, you have to use the matmul function, which will return you the matrix multiplication, assign that to a given array on the left side. Same thing, you have a scalar product for 2 vectors. And here's an example of how this can look. And one important thing with matmul is that you have to make sure that the value that the variable that you assign on the left side has the correct, the result of the matrix, the size of the matrix multiplication. It has to be the right size. So it will not dynamically allocate a return value. You have to declare that yourself in the correct size. So this is, otherwise you will get the memory error, or the program will crash. So Fortran, as I said before, Fortran compiles the code as machine code. And if you crash something, it will crash hard. There are no checks and for this. You have to make sure that the variables are the correct size. There are some compiler flags that you can enable that will check for the ranges of things. So when you compile, but when you run your optimized codes, you often remove these checks because you want the performance. You don't want to have the code checking all the ranges all the time, because that will slow your code down. There are some other routines for arrays as well. All, for example, returns true if all elements are logical value true. Any returns true if any element is any of the elements are true. You have max val and min val, which are calculates the max value of an array or the min value of an array. So it's very easy to confuse with the max function and min function, which are functions that determines the this max value of a given number of arguments. So in this case, max val means that it will calculate the maximum value of the entire array. So these are very optimized routines. So if you need to calculate max and min of an array, use these functions. Don't do your own loop unless you have very good reasons to do that. You also have a product function that will return the product of all elements in an array. Sum will sum all elements of an array. So here we have some examples here. Product of A will calculate the multiplication, or the product of all elements. Sum will sum all the elements. Max val, the maximum value of A, the minimum value of A, and so on. So it seems to be 0.98 is the highest value here, yes. And minimum is 0.12 something here. Yes, 129. There are some information routines. We already covered some of them. The size, for example, here, which we used before, that is returns the size of the matrix in a certain dimension. Shape will return two values in an array. Upper bound and lower bound can be used to check the maximum field index of an array. Let's see here, how 26. So here is, I have declared three variables here, one 20 by 10, 10 by 20, and also a C array with indexes starting from -10 going to 10, so 21 elements. And then I just check all these, use all these functions here to kind of see what they return. So let's see here, 26. So we start with the first one here. Lower bound A is 1. Let's see, upper bound. Okay, sorry, it's a two-dimensional. So the first dimension's lower bound is 1. The second dimension is 1. And then we have upper bound A, you get 20, which is the upper bound, the number max of the first dimension. 10 is the second dimension. And same thing with B, 1, 1, 10, 20. And then we check the C here, so -10 and 10. And then we have the shape here, you have 20 by 10, 10 by 20, should be correct. And then the size of shape of C is 21. And the size here, if you don't specify a parameter here, size will give you the total number of elements in the array. So in this case, it should be 200. Same thing for B, and the size C is 21. It can be useful sometimes, especially if you have subroutines that want to work on arrays and you want to have loop ranges, for example. You can use these functions to query those and get the loop ranges. So now you have most of the things you need for a program. And I think, so next we'll discuss how you can actually read things from different sources and write things in different ways. But we will have we'll do a 10-minute break, and I will continue after that. I need to get some coffee and water. So I will pause this here now. So this section I will go through how to get data into your Fortran code and also to write data out from your Fortran code. So reading and writing is done using the read and write statements. Read and write statements each write either read from one line or write to one line. The first parameter determines where to read and write, so basically the direction. So to which file or from to read. If you read from standard input and standard output, you can replace the parameters by using star. That will kind of use the standard input, standard output. Fortran will automatically convert text in a file into type variable. So when you read from a file and it reads a number, the number will automatically convert it to the variable that you read in. You can also read in several variables at the same time using a comma separated list of variables. There is also a way of, if you have very many items on a single line, you can use something called an implicit loop to read multiple values without specifying in a long comma separated list of variables. So here are some examples here. So read star star, that means we read from standard input. And then we have A1, A2, A3, A4, and so on. So the first value in the file from the standard input will be assigned to A1, and then and so on. This can also be replaced by AI I equals 1.8. So this is equivalent statements. You can use the same thing for writing here. So in this case, I do. I write here with instead of reading them. There is also a new statement in Fortran 90 which you can use to quickly print something on the screen. It's called print star, and then you can leave out the second star here, which is actually formatting, which I come into later, and just print something out here. As in Python, it's sometimes very important that the output is formatted in some standardized way. So for readability, or for the user, or for being able to read from files and so on. So the second parameter in the write statement is the format. And if you put a star there, it will use the default format, which tries to display all the variable at full precision, which can look kind of ugly on the screen and also hard to read. Instead of a star, you can specify a format parameter, which kind of describes the output format for you. And it's similar to what you do in the Python format statements as well. And you use, just like in Python, special codes to specify what kind of output you want. So common codes are A, which is a specified formatting for character strings. So you give A, it will be a single character. AN will be string with a number of with the width of n. You can specify I for integers, and then you can also give a field width of n here. So if you specify I4, it will try to output an integer with a field width of 4. Then you can specify a floating point j, where you give a width m and a number of decimals n. You can also repeat format codes by specifying a number, a prefix this code that will say to the compiler here, I will output 6 integers with a width of 5. And all the format codes need to, in the string, have a parenthesis around it. It's a bit strange syntax, but that's the way it is with Fortran sometimes. So you give a string with parenthesis 6i5. That is the format code. So in code, it can look something like this. I have 2 variables here, arrays. I want to print them out in a table. And in this case here, I first create a table header here. And this is just for illustration here to see how it looks. So I have 3 strings that are 8 characters width. So in this case, I have 1, 2, 3, 4, 5, 6, 7, 8, and then I have another one with 8, another one with 8, and then I have 4 strings with a character width 5, and these should be here like this. And then I write the numbers from the arrays here. So in this case here, I have the first parameters I want to output is 3, so A, 1, 2, and 3. And those are floating point values. So I want to have them, there are 3 of them. They should be 8 characters wide and 3 decimal points. And then after that comes 4 integers with the width of 5. And when you run this code, you can see here that Fortran will place them exactly like you expect them to. So the first floating point will be 8 characters, and there is 2 decimal points here. And the next one is exactly after 8 here, so it will fill here with spaces, and the next variable comes here. And then you have the integers here, and they will be padded to the left side here. So in this case, I have DDDD and 4. And the same thing here, there are 5 characters, and then you have integer 6, 7, like this. So this is the way, if you want to create nice tables, you need to work a lot with the formatting codes in Python, in Fortran. One problem is that when you have, sometimes you have values that can vary in size, and you need to kind of handle, let's say you want to create a right array function. And in that case, you don't know the sizes of the arrays coming in. So you need to be able to specify the formatting codes dynamically depending on the number of columns. And because the formatting code is a string, we need to kind of create a string that specifies the number of columns in some way. And the nice thing with the write statement is that you can use a character string as a file. So instead of putting a file, a number, or a star in the beginning, you can put a string and then write to that string. So in this case here, I create an empty string here with 255 characters, which will contain the formatting code that I want to use. And then I write to this string here. A character, an integer, and a character. So in this case here, I specify columns here, and the resulting output here will be the array coming in, and you get the size here, the columns here, and the formatting code will be parentheses, a string representation of columns here, and G8.3. And then I can print out here, and I can change the number of columns here, and the formatting code will be updated automatically. So let's see if I go into 29. So here I have a print array function here with the formatting code here. And I have added here a print statement here that just prints out the resulting formatting code. So we start by 8 by 8 here. So I have an array here, which I will initialize to random. And then I print it out here. So let's see here, 29. So now you see here that when I print it out here, it says 8J10 by 5. So by using this technique here, I can create any formatting code depending on the input. So if I change, for example, here to 7 by 7 matrix here instead and run this. You see here it created a formatting code 7J10.5. So using a string as the first parameter in the write, you can actually do some string conversions like you do in Python with formatting here. And this is the kind of only option to kind of combine strings in this way using the write statement here. So it's keep that in back in your mind that you can use the write statement with a string as well. So now we just, all the examples I showed you wrote things to screen, or read things from the keyboard. So if you want to write to files, you need to associate a file with a handle. Same thing you do with Python. In Python, you've got an file object which you use to write to. In Fortran, you will get a number, basically a unique identifier that you use to kind of associate with an actual file on disk. And you do this association using the open statement, just like in Python. And that does this kind of association between the file and the identifier. And then you use that identifier as the first parameter to write or read in your code. There are three modes of operation, file operation modes in Fortran. There is the basic text files, which we have done using the previous examples here. There is something called namelist.io, and that is a text files containing named variables. So it's kind of nice for input files to your code, for example. And there are binary files or unformatted I/O. I will cover those in separate examples here. So also, when you are done doing I/O, it's very important that you close your files. That indicates for the operating system that we are done using the files, and the operating system can do some caching, or it can write down to disk. Most of the times when you write the files and the operating system, they will be written to memory first. And only after a while they will be written to disk, so there's kind of buffering going on. If you don't close them, the operating system is not sure if the files are open or not, and they can also leave files dangling when the code closes. So it's important that you close your files when you're writing to them. Opening files, here I have a statement here, so it's open. We need to give it an identifier here, and I usually declare them as constants like this. So I have integer parameter in file 15. Those numbers can be anything. They have to be unique for the same file. So open unit in file, the file name, the way you want to operate on the file, in this case sequential, that means text file mode, and what you want to do, read. So it's very similar to what you do in Python, except you have to specify a little bit more verbose here, what you want to do. So if you want to write, you put write here, which I see before. And then you take this identifier constant, and you use that as the first parameter to read from the file. So this indicates for Fortran where to kind of find the data. So you can have multiple files open, you can do read and write simultaneously from different files. And you give them the identifier here, and it will read. And here I close my file as well to make sure that I'm not interested in this file anymore. Writing is similar, access sequential. Difference is that you specify write here, and then you use the write statement to write to this file. There is also a mode action called append, which will add things to your existing files. If you want to read from the keyboard, that we already did this. So star, that means reading from the keyboard. And the keyboard has hard-coded actual numbers, and that is also for legacy reasons. So a long time ago, in some galaxy far, far away, they decided that 5 was the keyboard. So if you want to read from the keyboard, it's 5. So don't use 5 as your file identifier. That is important. Also, so that there should be screen here. Okay, writing to the screen is the star by default. There's also a hard-coded number called, which is 6, which is standard output. So don't use that in your identifiers. Unless you want to kind of check your output in some way, then you can, if you give it the number 6 and write, the file will be written to the terminal instead, and you can kind of verify what is actually written to file. So that was basic file management. I will come back to binary files later here. So first a bit about code structuring. I already mentioned modules and main programs, and so this is just maybe how do you at some point your project will grow, It will grow so large that it's difficult maintaining a single source code file or multiple source code file or subroutines. But it grows large, and to maintain code, you need to kind of divide your code up in maintainable parts. And the key here is using modules. And you should try, before you start coding or reorganize your code, use pen and paper to lay out your blocks of your code, the functionality of your code, and then organize your subroutines and data structures in logical modules. So for example, if I take the example again from my finite element program, I have my main program, and I divided up my code in different modules here. So I have one module here is for reading input data. I also have another module for writing output data. I have my finite element functions in the FEM module. I have my solver in a special module called solve. And then I have some routines that are common for all of my modules here, which I put in utils. It could also be constants, for example. So it could have a module called constants as well that is used by all modules. And that could be, for example, all these precision constants that should be the same in an entire program. And that could be good to put in a specific module for that. So here is an example here. So the actual code structuring. So in this case, in my main program, I have use input data, output data, FEM, and solve. So this is the main driver of my program. And then I have my module 5. It uses the utils module here. So it will point to this utils module here as well. So in this way, it's quite good to structure your code, and then the main program becomes smaller and easy to grasp and understand. And then also it's easy to maintain the different modules. You can have several authors of your modules that work independently from each other in different modules. So a bit more about subroutines. Some newer things has also been implemented in Fortran 90 that can be good to know. So we did an example in Python where you passed a function to a function. And this is also possible to do in Fortran. You need to declare, if you want to pass a function to a subroutine, you need to declare that function as a kind of variable declaration in your calling subroutine or in your implementing subroutine. So in this case here, I want to create a code that tabulates a table, and and I want to let the subroutine not be dependent on any function. It should be able to take any function and tabulate that. And in this case here, I have my function here, and it just computes the sign of x and returns that. To be able to call this use this from this function here, I need to declare how this function looks like for the subroutine. So the subroutine knows how it should call this function. And in this case, I declare an interface here, and basically just define how the function, the template for this function that comes in. So you can compare it to, you have to make a function declaration instead of a variable declaration. And then you can use the function here, this name instead of my func here, in this one here, like this. And then you can, when you have your own function, you can pass the my function pointer to this routine here. It's a bit more complicated in Python, but it's doable, and it's not too complicated. Another really nice feature of Fortran is that you can provide, just like in Python, you can have keyword and optional arguments to your subroutines. This was not possible before Fortran 90, so this is a new feature your feature. What you can do is in your subroutine declarations, you can add an attribute called optional, and that means that this variable is not required in your subroutine call, and you can test for presence of this optional variable using the present statement. And you can also specify the arguments with keywords. I showed you the open statement before. We have this unit equals to and file name equals to. Those are keyword arguments, just like in Python. So here I have a subroutine that can order ice cream. So in this case here, I have 3 parameters: number, flavor, and topping. And I have 2 optional arguments. So flavor and topping, those are optional. And I can test for optional here using the if present flavor, then I know that this is given as well. So this routine can be called in any way. So you can call them just by specifying 2. The first argument here, the number. You can call it using 2 arguments, number and flavor. You can call it with 3 arguments, number, flavor, and topping. You can also call it with keyword arguments. So if you don't want to give flavor but want to give topping, you actually need to specify the keyword argument topping here as to be able to know which argument you specified. And the key here is that you can check for the arguments if they are available using the present function. And this will give you kind of really nice options to create an easy to use interface to your computational code by leaving out some of the arguments here and having default values, for example, for these variables. You can also overload. Procedures can be. You can have the same name of procedure that has different implementations depending on the data type. So basically, you can divvy up the work. So you have a main subroutine, an interface that says that this routine is for the integer version is called something, and the floating point is called something else. Let's see here. So it's better to show this in example here. So in this case here, I have a module here, and I have 2 functions here in my module. An integer function that will do something if it's, and the argument is an integer. I also have a floating point function called r function, which has a floating point argument. This is also something I haven't mentioned too much here. Intent in is a way of telling Fortran that this variable is only going in, it is not allowed to be modified. You can have intent out, which means that you are allowed to modify it. So you can add this attribute to make sure that the variables are not modified. Anyway, so this function is when x is an integer, this is when x is a floating point. I can combine them together to a single function, and depending on the data type to this function, it will call either ifunc and rfunc. So in this case here, to do this, I do declare an interface function here, and module procedure ifunc, rfunc. So you just declare which functions it can choose from. So depending on if you call this function here with a floating point, it will call rfunc. If it's an integer, it will call ifunc. So in this case, my main program will be like this. I use special here. I have 2 variables, one floating point and one integer. And in this case, a equals to function a. It will call the I function version. If it's a floating point, it will call r function here. And you see here that it will call 2 different implementation of this function here. So this is a really powerful function as well to be able to create subroutine libraries that have that you can call with different data types, and it uses different implementation depending on the data type you have, the user calls your subroutines with. Another cool feature that also was implemented in Fortran 9 is operator overloading. So you can actually define different operations. You can define what is going to happen if you have your derived data types. You can redefine the normal Fortran operators to do very specific things. And the syntax is type and your derived data type, the name of the function, and then operand 1 and operand 2. So in this case here, I want to implement vector addition, and I've declared a derived data type called vector, which is contains 3 floating point components, and then I want to redefine the addition operator. So the interface operator plus, and I say that this should be implemented using the vector plus vector subroutine or function. So in this case, I have a function called type that returns a vector, and it has 2 parameters, vector 1 and vector 2, and then I add those components together and return that out from this function. What I now can do is this, so I can declare 2 vectors or 3 vectors here, assign the components, and then I can do something like this. So now when I use the plus sign here, it will actually do the vector operation earlier here. So it will call this function here. So it means that you can implement your own algebra for different data types. This is something that has only been possible in language like C++ or Java before, and now you have this in Fortran as well. Public and private, we already looked at that. So in this case here, I have a private function, a public function, and I declared here the private function here to be private, the public function to be public. And if I try to, in my main program, call the private function, you will get something like this. So when you compile it here, actually, it will not find a link to this function. So it actually is actually not impossible to compile a program where you call a private function. It's that invisible. Pointers I will go through quite quickly. It's very complicated subjects, and I have a chapter on that in my book as well. But basically, a pointer is a reference to a variable. And in Fortran, pointers are strictly typed. You also need to specify attribute target to be able to assign pointers to a pointer. There is a operation called nullify to disassociate the pointer from a target, and the equal sign greater than is used to associate a pointer with a target. So it's a kind of, it's very strict. It's not like what you do compared to C and C++. This is very strictly defined pointer operations in Fortran. It's not very. It should be more secure than using raw pointers that you do in C, and C. So in this case here, I have a allocatable array A, which is a target. That means that this variable can be associated with a pointer. So that is only what this is what the target attribute means. Is that you can actually assign this to a pointer. And then I have 2 arrays here that are pointers. So those are 2-dimensional pointers to B and C. We haven't created them. I allocate A 20 by 20. Now I associate B with A. So now B actually points to A and should return the same size. We will check that soon. I also have a create array here that has a pointer here, D. So by using a pointer here, I can actually allocate an array inside a subroutine, and it will be returned out as a pointer. And then I print C, and that should also the same size as, no, it should be 10 by 10 now. So it's 10 by 10 array. So when I print it, it should be 10 by 10. So I deallocate C, and then I disassociate pointer B. So now I don't want to point to A anymore. I just assign it a null. And now this here is not possible anymore. So if I try to use B now, it will point to some place in memory, and you will probably get a there's an old Windows XP dialog is kind of that this program has encountered an error and needs to close. So you are kind of, when you're using Fortran, you're kind of really low-level hardware. So if you access something outside memory, the operating system will complain and kill your program. So finally, we'll look at some of the more advanced I/O operations you can do. So we already went through text operations, read and writing from text files. There are some standards here. So when you write data to the screen or to a file, complex numbers will be surrounded by parentheses. String must be enclosed by quotes when output, and you need to kind of specify the same format when you want to read the data again. So in this case here, I have, let's see, I open the file list of txt, and I write data to this file. So A, B, and if I want to have a string in this, I need to kind of write out double quotes here, topping, and this will write something like this to the file. So 42, floating point, string. If it's a logical variable, it will write either F or T. If it's a complex number, it will write a parenthesis and a complex component here and end parenthesis like this. What you also can do when you, if you want to write something that is more kind of editable by a user, you can use something called name list IO. And that means that you read data from named variables or values in a text file. You need to define these names in a name list. And a list of name, and in the file, the name value pairs are separated with commas. So it looks something like this in the file. Name equals a value, name equals a value, and end like this. It can contain arrays as well. And if you write to a name list, it will recreate this value name value pairs automatically for you. So here I have a file here, a name list. It's called food, and it just defines the names that I want to use in my file. So in this case, I mimic the same variable, use the same variable names in the name list. And those will refer to the actual variables here as well. So when you read from this file, you specify where you want to read from, and you specify the name list, and it reads all these variables from the file. And same thing if you write the other way around, you specify a name list, and it writes all those variables specified by the name list. I thought I have some. Let's see if I have. So let's see if we can build this one. First, I just need to give so if we look at this directory here. So this is the output from, let's see if we can zoom. So it says the name list is food, and then it lists number of eggs equals to 12, liters of milk is 5, kilos of butter 42, and the array list is like this. So this is the, and you can of course edit this by hand as well. Fortran will read it in those variables. Very nice function. So just to kind of just go through some of the new features that you have in Fortran. So as I showed before, when you wanted to create an array inside a subroutine and return it back, the only options before, I think 2003, was to have pointers. And now there is a way of, you can create arrays inside a subroutine without using pointers. So you can have allocatable arrays as dummy arguments in your subroutine. So here is an example here. So I have a real allocatable intent out a comma as an array colon comma colon. I can do an allocate here, and I can declare my real allocatable a in my main program, call create array, and this will be assigned and created inside a subroutine. This was not possible in Fortran up to Fortran 95. The same thing with functions. You can have a function that is create vector. Here is a real allocatable dimension colon. So this is a vector, and I create the vector here, and it will allocate it here and return it back. But also by a nice way, so you can implement your own allocation routines that does some initialization of your data structure as well. Another thing that would be quite obvious but isn't is that you, in your derived data types, you can actually have allocatable arrays. This was also not possible before. This is also a new feature, which enables you to kind of create really dynamic data structures in a very, it's a very nice feature. However, you need to kind of so these will be also automatically deallocated. But earlier, if you use pointers here, you needed to deallocate yourself. Submodules is also something new. So, for example, if you have a really large project and you realize that some of your modules are growing really large, you can actually divide up this large module into several submodules, but it will still be perceived as a single module. So in this case, I can create something called a submodule here that implements a certain thing and have this as a separate source code file. Another very important features that have been sought for a long time is being able to interoperate with C, and that wasn't possible before until the newer extensions came out. So now before there were really no clear definitions of what data type actually could be used with C. If you were on an Intel platform, it was much easier because the real 8 corresponded with a double and so on, but that was not necessarily true on other platforms. Also, C is a very important language in high-performance computing and in other computing-intensive applications. And so it's very important that you can kind of combine both Fortran and C in a single program. What has been added to Fortran is a special module called ISO-C binding. And it defines all the C data types so that you can use them in Fortran. So you add the use ISO-C binding module to your code. Then you have all the C data types available. So you can do integer C int. That will be a C integer variable. You can do real C float. B will then be a floating point C variable, the same type. So now it's much easier to define interfaces and interoperability with Fortran, because you can actually have a data type that exactly corresponds to the C data type. There is no confusion in this. This is like it should be. And that also means that you can declare subroutines using these data types, and you can be guaranteed that they can link together. Another thing that was added was the ability to declare in your subroutines argument that uses the same calling convention as C. That means that you can say that this variable should be passed by copy or by value, and then you can create identical subroutine declarations that can interoperate with C. So you can basically link directly with C. And I don't have an example of that, but basically there is a value attribute that you can add to your variable declarations that will mimic the standard calling convention in C. Another thing that was added was, I think it's in 2003, was object-oriented programming. So now you can do most of the things you can do in C++, you can do in Fortran as well. And the idea they extended was the derived data type has now been extended so that it can use, you can add both data and subroutines to, and basically creating a class. So type my type here, that this corresponds to a Python class. Real my value here is an attribute that is assigned to this variable, this class. And then you can define the class methods here under a contain section here in the derived data type declaration. You can also assign which routines should implement this routine here by specifying right and then point to the implementation of this routine. And you implement this is a bit, takes a bit, it's similar to what you do in Python. So I have subroutine write my type. I have this here, which corresponds to the self attribute in Python. And this here, you have to declare this is of the type my type, and so on. And yeah, basically this enables you to do object-oriented. And there's a whole chapter in my book on this. There will be no assignments on this, but it's something you should know about, that you can actually do this in Fortran. And you use this class by, you can do call, define class here, and then you specify your class name, and X here will be an object of the type M type. And then you can call X, and then instead of using the dot operator, you use percentage or right here. So it's very similar to Python, except that you use a percent operator instead of a dot. Another thing that would have been quite obvious for many other computer languages is to be able to access the compute environment. So up until I think it was 2003, you couldn't get the environment variables from your source code. But now you can, and there are you can use the function called get environment variable. That will return you the value of a certain environment variable. You can also get the number of command line arguments, also not possible before. And you can get the specific command argument as well by using the get command argument. So this was my final slide for the Fortran part. Next week, I will go through some tools you can have to structure your code and create an efficient build environment. I will also go through how you can compile Fortran code that can be used as modules inside Python. So using a tool called F2Py. So it will be a bit mixed language programming next week. So that was it.